This lecture is the first half of our coverage of the ideas that we've gone so far as applied to solid state physics. We're going to focus in the slides that follow on understanding what energy bands are and what their origins might be and how we should think about them theoretically, and how we can use band structure, the details of the electronic states for a material, as represented in what's called a band diagram. And that tells us how electrons respond to applied electric fields, for example. And then in the next portion, the next lecture, in which I'll talk about more ideas in solid state physics, I'll talk about application of these ideas to understanding conduction in materials, and then focus on the ramifications for semiconductors and semiconductor devices. We will cover these other topics, but with relatively little depth. So our plan here is to start out talking about how we get from atoms to solid state energy bands. You already have a bit of an idea of that, and I'll try to display that to you. And then out of the way that we interpret what goes on in solid state energy bands, we'll come up with a way of expressing a relationship between the wave vector and the energy of an electron in a solid state material. That relationship is called the dispersion relation. We will then, in this portion of the lecture, focus on some of the approaches that allow us to deduce what the dispersion relations look like. And then in the following lecture, we'll talk about the ramifications for the measurement of properties, that is the conductivity of materials, of metals and semiconductors, and an application to the simplest yet very complex device, which is called the diode. So as a reminder, we've already begun talking about what happens to wave functions when we put two atoms side by side. And we talked about two extreme cases where the wave function on one atom is exactly in phase with the wave function of the electron on the other atom. And as a result, we get a wave function that has sort of a maximum in the middle here and then goes off to the two sides. And then the other extreme is when the wave function on one atom is exactly 180 degrees away from the function on the other atom. It turns out that this state here, A, is of lower total energy than the state B, in which the wave function has to go from a maximum here to an anti-maximum there. And so it turns out that the overall curvature of the wave function here is greater than the overall curvature of the wave function there. So we have the idea that the energy level is going to depend both upon the atomic state that we have on each of the atoms. So the atomic state in this case looks like that. Okay, over here it would look the same. The atomic state is the same, but the way that we add the states together in adjacent atoms does change the total energy. So what about bands in atomic levels? Here's a graph that I showed you a while back of a way of thinking about the energy of a molecular state as a function of the distance between the atoms. And for molecular states that are very tightly bound to each individual atom, like this one here, then we can bring the atoms pretty close to one another, and it doesn't lead to any differences between the energy of two states in which the wave function is out of phase on the two neighbors. Right? Whereas if we go up into higher energy states, then it will turn out that the electron actually has strong overlap in being located on one of these sites, but then the wave function doesn't go to 0, and it actually has some component on the next site over. And when that happens, the energy difference between a state that oscillates as it passes from one atom to the next can be large compared to one that oscillates in phase or one that has the same phase on each of the atoms. So from the previous slide and this slide over here, we have sort of a simple picture of when we have just two atoms in a system. When we bring the atoms close together, the states split into a bonding and an anti-bonding state. And if I have three atoms, then the states split into three states. And when I have 1, 2, 3, 4, 5, 6 atoms in our system, as I hope we're showing here, 1, 2, 3, 4, only 5 here. So when we've got 6 atoms in the system, then we have a number of possible states that I'm going to describe in more detail on the next slide. Here is a cartoon that illustrates the way that we can think about energy bands in solid. In this case, I just have two atoms where those two atoms are far apart from one another, or, as we showed previously, when they're very close to one another so that the electron states can overlap. So in the tight binding approximation, or the linear combination of atomic orbitals combination, we would look at the wave function for each of these separated atoms, which for the ground state looks something like this as we take a cut in one dimension across the atom. The ground state looks like this, and if the ground state on the neighboring atom is the same, then the ground state will have exactly the same shape, and we have a choice. This wave function here can be 180 degrees out of that wave function, apart from that wave function, or it can have the same energy. The same phase. So here's 180 degrees separation between the two atoms. Here is both atoms in the same phase. In both cases, we can put two electrons into a state, and if the state is all in phase, then I get one energy for this system. And if the state is 180 degrees out of phase on the two atoms, then I get another energy. When the two atoms are far apart, that doesn't influence the energy very much. But this third case, I put the atoms very close to one another, and as a result, the wave functions actually overlap with one another. And in this case here, the upper case, the two wave functions on the two atoms are in phase with one another, and in the lower case, they're 180 degrees out of phase with one another. Those two states have different energy, so that is illuminated here. So what happens if I've got three atoms? How can I combine my states? Again, on adjacent atoms, I can put them out of phase with each other. So here I've got three atoms far apart, and they're all in phase. And the wave function then looks like that. Here, I can take an atom on the end, and I can flip the phase of that one atom. And then my wave function looks like this, sort of a combination of low energy linear combination and a high energy linear combination. And then finally, I can flip the phase on adjacent atoms so that I get I'll call this zero phase, 180 degrees phase, and back to zero phase again. Then the phase between adjacent atoms is changing, and the wave function looks like this if these are 180 degrees out of phase with one another. So in this case here, when I have three atoms, it turns out that the three states on the atoms end up combining and then separating to leave me still with three states, but now the energy of the states depend upon whether I have differing phases on adjacent atoms or the same phase. This is the lowest energy state. This is the highest energy state, made up of these wave functions on 3 atoms. So here's an example of when we have 6 wave functions. And in this particular case, the quote-unquote solid is terminated here. So the wave function has to go to 0 at the boundaries. But in between, I've still got my atoms. And if all of the wave functions on all of the atoms are in phase with one another, then I get positive, 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 positive. It's a relatively smooth overall structure where adjacent atoms have the same phase. Now, if I take those adjacent atoms and flip one of the ends, the phase of one of the ends, then I go from the ground state to the next state up, because this combination down, 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 up, down, is going to be of higher energy than this state here and lower energy than this state, because we don't have to flip as many times. So the highest energy is this one, and the lowest energy is this one here. And that's a 6-atom wave function. We're going to talk about matching these ideas up to a sample with effectively an infinite number of atoms, so an infinite number of wave functions to make a very, very, very large solid. Now we're going to extend the ideas from the 6-atom array that we had on the previous slide to a system in which we have a periodic array of atoms that extends from minus infinity to plus infinity. So this is a large sample, let's say, and the atoms are arranged periodically. So these dots would represent our atoms, and the potential that the electron sees for each of these atoms would be represented by a cartoon here of the Coulomb potential. And if we focus on one of these atoms and ask what an electronic state on one of those atoms might look like, this might be an example down here. So for each of these atoms, there is a solution to an electronic state at a certain energy, and because the potential is identical at every one of these sites and the sample goes on forever, then the wave function at each of these sites has the same structure. And the only difference between the wave function at one site and another site will end up being a time phase factor as a wave travels through the sample. So the solution to the Schrodinger equation on this atom looks like that. Solution looks like that on the next atom, and the next atom, and the next atom. This is the portion of the wave function that exactly repeats on each site. The actual solution has been proposed by Bloch, and it's called the Bloch theorem, and it is that the wave function of electrons in the solid overall is a product of the wave function solved for each individual atom, like so, the wave function on each atom, times a phase factor where the phase of this state, remember that we're just representing, for example, the real part of the wave function here, or we might be representing the magnitude of the wave function, and there is a time-dependent e to the I omega t, and there is a space-dependent phase that could influence the phase of the wave function on each of these sites. Remember, the magnitude is the same on each site. It's only a question of what the relative phase is. And we're just looking at, let's say, the real part. So in looking at this overall result here, we are seeing the wave function on each side multiplied by an e to the I kx phase factor, where the phase on this side is different from the phase on this one, different from the phase on that one, all right? That the overall wave function is a repeating wave function, u of x, where u of x repeats at each side, times e to the I kx. This k is called the wave vector of the wave function. So the wave vector is what changes the phase between the atoms. And that the way in which the phase changes from atom to atom, we already learned, determines the relative energy of the state. So for example, here, if I just flipped the phase of one state at the end, then I'd have one energy. If I flip the phase of a state toward the middle, then I'd have a different energy. And I have all different combinations of phase relationships. All of those possible combinations of phase relationships can be expressed in the variation of the wave vector with position, e to the I kx. So for a given k, I have a given rate of change of wave function in the sample, and that gives rise to an energy within the band. The band itself, what band we're looking at, is determined by the repeating part of the wave function, or the wave function on each atom. And then within the band, the energy varies. So we have a energy wave vector, what's called a dispersion relation, where the energy of a given state in the sample depends upon the band that you're in and the wave vector of the state. And the relationship, that relationship between energy and wave vector, is called the energy wave vector dispersion relation. So we've seen this several times before, and I'll just write it out here, that the energy of a given state is an energy that depends upon the wave vector for that state. How does the phase change from atom to atom? And we already know something about dispersion relations, where we know that the kinetic energy of a free particle is h bar squared times the wave vector squared over twice the mass of the free particle for a non-relativistically moving particle that has mass. For a photon, massless particle is moving at relativistic speeds, the energy of the photon is equal to h bar times the speed of light times the wave vector. So I've got two different examples of a dispersion relation, which tells us how the energy depends upon the wave vector. In solids, we have some very interesting energy wave vector relations, right? So when I have a plot here of the energy of a given state as a function of the wave vector for that state, so wave vector on this axis, energy on that axis, and within a given band, we find that when the wave vector is 0, then that means that the phase of all of the states across the entire sample is the same. That's the lowest energy within that band. And then as we increase the wave vector, we start changing the phase of adjacent atoms more and more and more, and the energy of a state goes up. We're going to see later on why it is that we end up with these other relationships up here, but so far, in here at least, this looks, for example, like a free electron propagating in a material. And the way in which the energy changes with wave vector depends upon which direction you go through the crystal. So there are 3 possible directions expressed here, and the details are not important. It's just that the energy depends upon the direction that the wave vector is changing in the material. So we could think of this as kx, ky, kz, for example. And again, these plots that we have here are called energy band diagrams or dispersion relations. And these, again, tell us how the energy of an electron in the system changes as the wave vector changes. In this particular case, this band that we're looking at here is essentially the 4s state of the potassium atom. And the 4s state is actually half filled because there's only one electron, and the s state can hold 2 electrons. So it's half filled. And as a result, we make a drawing here that shows a band which, when we work it out, turns out to be approximately half filled. And we see that the Fermi level in this system sits in the middle of a band. And as a result, it's possible to take an electron that has this wave vector, give it a little bit more wave vector, and it gains a little bit more energy. And by our ability to increase the wave vector, we've accelerated the electron in the system. We've increased the momentum. So this particular material is a metal because we have a partially filled band, and it's easy to take an electron and give it just a little bit more energy and a little bit more momentum by applying a field. I've expressed the filled states here, just those states there, as those that are in the colored region, in the shaded region. Metals have a partially filled band, as I mentioned. This particular figure only shows the 4s state. There are more states down below, but we're just really worried in many cases about the behavior of the system when we apply a field, so we need to know the dispersion relation about the Fermi level, near the Fermi level. I point out that near the bottom of the band, we see that energy as a function of wave vector looks parabolic, that is, that it's a constant times k squared, but that constant might not be what we had for a free electron. It will not be. And then one additional note here, which is that photons carry very little magnet in terms of the magnitude of their momentum. And as a result, an optical transition, so for example, if I shine light into this system and the light interacts with an electron of a particular wave vector, what will happen is that the electron can be excited directly upwards in this diagram, where the photon wave vector is so tiny compared, remember it's 2 pi over lambda, is so tiny compared to the electron wave vector that it looks like a vertical transition in this diagram. So we can go from state to state, and that's an allowed optical transition. So there's a lot of information in plots like this. There's our vertical transition for an optical excitation in the material. Light comes in, photon is annihilated, transfers energy to the electron with very little momentum transfer. Here's another material. In this case, it's silicon. And once again, we're not showing all of the states in this material. Each of the bands that we see here, each of the lines that we see here, corresponds to a particular type of bonding or atomic state in the material. And this might be some combination of s orbitals and p orbitals in here, for example. But each one of these bands that we're looking at corresponds to an original atomic or molecular bonding orbital. And then we vary the wave vector to look at how the energy varies as we change the wavelength of the phase, right? In terms of interpretation again, states on this graph below 0 are filled states, and states above are empty states. There is a band gap here between the top filled state and the bottom empty state of about 1 electron volt. This actual calculation is quite old, so it's not very accurate. It should be about 1 electron volt from here to there. That's the band gap of silicon. And once again, the way in which the energy changes with wave vector tells us what happens when we attempt to accelerate an electron in the system. How does the energy of the electron change? This particular material, because the Fermi level ends up sitting between one band of states and another band of states, is an insulator at low temperature. At higher temperature, it becomes more conducting, and we frequently call those materials semiconductors. So what is the relationship between the band diagram that I've been showing you and how electrons actually move when we apply the field? So we can write down a relationship that tells us the relationship between, in the end, we'll look at the acceleration and the rate of change of the momentum. So we apply a force that could be an electric field, for example. And as a result, the momentum of electrons in the system change. And we can write that as h bar dk dt because momentum is h bar k. We also know that force is equal to mass times acceleration. And acceleration for a wave packet particle is the rate of change of the group velocity with respect to time. So mass times acceleration. And for an electron that's described by a wave packet, we know what the group velocity is. It's the rate of change of the frequency of this traveling wave, which would be the energy of the traveling wave, with respect to the wave vector. And then we can just write that out by making the substitution for omega. 1 over h bar d energy, d wave vector, dE, dk. That's the group velocity, so we can put that in there. The acceleration then is the rate of change of the group velocity with respect to time. We go ahead and take that derivative, and by doing a chain rule derivative, we have that the acceleration is 1 over h bar, second derivative of energy with respect to wave vector, dk dt. So just repeating here, that's the acceleration. So force is equal to mass times acceleration, or force is equal to h bar dk dt. Go ahead and solve for that, and we find out that the acceleration in the system is related to the force via this factor here, 1 over h bar squared d squared e dk squared, second derivative of energy with respect to wave vector. And by analogy, we look at this equation up here, F equals ma, and we look at this relationship that we just derived, right? And we, by analogy, say this must have dimensions of mass, and it does relate the force to the acceleration. So we're going to call this term here the effective mass. So we try to accelerate in a particular direction. We need a force to make the electron accelerate, and that relationship that tells us how much force we need to get a certain acceleration is called the effective mass. The effective mass is equal to 1 over h bar squared d squared energy dk squared, second derivative of energy with respect to wave vector. What this is the curvature of the band diagram of the dispersion relation. You can see, by the way, that if E is equal to h bar squared k squared over 2m, that if I actually take that derivative for a free electron, I end up with m star effective mass is equal to the actual mass of the electron. So it works for free particles at least. So the effective mass is related to the curvature of the energy wave vector relationship. And that curvature, as you previously saw, can be positive or negative. We'll talk a little bit about where that positive or negative curvature can come from in terms of mathematics and theory. And what we actually know is that near the conduction band edge, the energy as a function of wave vector actually looks like the conduction band energy there, and then a term that is related to the propagation of the electron through the material. We end up having something that looks like a parabolic band near the conduction band edge here, right? And I should not have an H there. This is h bar squared over 2m of the electron, right? And then the effective mass of the electron is related to the second derivative, the curvature of the wave function. If the dispersion relation is parabolic tilted upward, right, so cupped upward, then the effective mass is positive. If the dispersion relation curves downward, then we say we have an effective mass, which is negative. And here's how the energy near the band edge of the valence band looks. And it actually does curve downwards. In many cases, it curves downwards. And so we have a negative effective mass. So in a solid, we can have both positive and negative effective masses. That's not the real mass of the electrons, but it's the mass of the electrons. It's the response of the electrons to an applied force. That is, we apply a force in a given direction, and the electron actually moves in the opposite direction to that which we expected. And that's because the electron is interacting with the force that we apply and the potential of the crystal. So the crystal is picking up momentum. We call these positive and negative effective mass particles electrons when the mass is positive, and holes when the mass is negative. And again, that effect, the reason that we have an apparent effective mass that is negative, is that momentum is taken and given by the lattice of ions itself. So the semiconductor and solid state jargon word hole means an absence of an electron from a normally full electron state. You can think of it as a bubble where an electron is absent, okay? We can assess the properties of the hole by taking the total wave vector of a filled band to be 0, and then we take one electron out, then the momentum total wave vector of all of the electrons in the system is 0 minus the momentum of the electron that we took out. So the momentum of the system is opposite to that of the electron that we just took out. The velocity turns out to be the same as the missing electron, but the effective mass is negative. The equation of motion of a hole with an applied force is that of a particle of positive charge. Holes are actually relatively easily created in solid state materials. We can have an optical excitation, for example, which takes an electron from a lower energy band to a higher energy band, creating a hole in the lower energy band. We can have thermal excitations between bands that leave holes in the lower band and electrons in the upper band. Whenever we create a hole, we have to have an electron that's put in another band. We're going to talk in a later class about how we can control the number of electrons and holes in a material by adding dopants to the material. And I'll talk about conductivity more later on in this course. At this point, I'm going to switch somewhat over to the concepts that are behind how we can understand the origin of band structure and how we can estimate the behavior of the bands in a system, what the dispersion relation might look like. In solid state physics, very little is directly computable. We run into computational limits. We could start with the Schrödinger equation and put in all of our potentials and attempt to calculate the energies of all of the electrons in the system as a function of wave vector for the electrons in the system. And this computation begins to get very massive as soon as we get more than about 100 atoms. I think that typically now computations with supercomputers can be done on thousands of atoms, but still it's just thousands of atoms. So to actually compute the properties, we make approximations, and then we check to see how well our measured properties agree with the computation. And we tweak the computation then. Maybe we change the potential a little bit in order to make it match the measurement. This approach is called a semi-empirical approach. So we have a theory, but then we tweak the theory, we tweak the numbers in the theory in order to make it agree with experiment. Then once we've got a set of relationships that agrees with certain measure properties, then we can look at the dispersion relation and try to figure out what the other properties of the material might be. And then we can predict how something would respond when we apply an electric field, for example. So I'm going to talk in the next few slides about methods of approaching and understanding the dispersion relations, calculating the band structure. There are three important regimes. What I've got here is a cartoon of the potential, and then three possible energy levels that could be solutions to this potential. In one case, I have an energy level which is deep inside of the potential, and as a result, the wave function that would sit on this energy level would be quite confined, and the interaction between the wave function on this atom and the wave function on that atom is going to be small. The overlap is going to be small. That type of state can be approximated using what's called the tight binding or linear combination of atomic orbitals approach, where we solve for the orbital on one atom and then look at perturbations when we allow the orbitals to overlap from atom to atom. I'll talk a little bit about that next. So tight binding is the word for that kind of calculation, where we assume that we have pretty much an unperturbed orbital on one atom, and then we just look at overlap, probability that an electron can hop from one atom to the next. And when the energy of the electron is very large, much greater than the binding energy on the on each individual atoms, so that the energy level is well above the potential, then we can think of the electron at this very high energy as behaving pretty much like it's free, but with some perturbation due to the fact that there's an underlying potential, right? So this is called a nearly free electron model, where we take the periodic potential to be a very weak periodic potential. We'll talk a little bit about that, and we will use a very simplified model to get some idea about what happens in situations like that. And then we have intermediate energies. So if I had an electron at an energy here, then it's clear that that electron is going to be strongly influenced, the wave function is going to be strongly influenced by the presence of the potential, all right? This would be a bound state, but the wave function on this atom is going to overlap strongly with the neighboring atom. And so the actual solution to the wave function on a particular atom is going to be strongly influenced by the presence of the nearby potential. And so this problem is a very hard problem and tends to require sort of the full Hartree-Fock type calculation that we talked about for single atoms. This is computationally very intensive, and we're not going to talk about the solutions for electrons in this energy. We'll talk about very strongly bound electrons and very weakly bound electrons. So first, the tight binding picture, where the electron state that we're looking at is one that is at very low energy in the system, and that the wave function is strongly localized on each of the atoms in the system. And then we just think about whether there's some probability that an electron can hop from one state to another, from one atom to another. And so this is sort of a semi-classical approach where we have our overall wave function being the sum of wave functions on each of the atoms, right? And then we ask how much wave function do we have on each of the atoms. So the amplitude that the electron is on atom N is going to be the overlap with state N with the overall wave function that we have for the system. We start out thinking about the electron being on one atom, and then we look at the probability that it will jump to a neighbor. And we're going to take an amplitude of I times some number divided by h bar to give us the amplitude per unit time that it will jump to the neighbor. And then we can look at the rate at which the amplitude for an electron on a site N changes. And in the end, we're going to get a relationship between the overall energy of the state and the rate at which electrons jump from one site to another. We look for solutions in which the amplitude on a particular atom varies with time. That depends upon the energy. And we want an electron that a state that's going to be extended throughout the whole crystal, and all of the states have the same energy. So this energy in here is independent of N, but I have an amplitude on each of the atoms. That rate equation that we had on the previous page looks like this. Basically, we're just hopping from each of the adjacent atoms to the atom of interest, right? So the new amplitude is going to be related to the amplitude at start times the probability that we hop to and from neighboring atoms. And then actually writing it out in terms of the positions of the atoms where the atoms are separated by distance b. And we've got now a difference equation here, and we can take a trial solution and see what that results in. What we find, once we've plugged all that in, it's relatively easy arithmetic here, is that the energy of the state, which remember is made up of wave functions on each of the atoms in the system, is the energy of the state for an electron localized on one atom in the system. And then I've got a term here which depends upon the wave vector, the way in which the phase changes from atom to atom, and the amplitude of the hopping. This will turn out to be some overlap integral. How much does the wave function on one site overlap the wave function on another site in the sample, adjacent sites. That's A is going to be proportional to that. And I now have a dispersion relation that relates energy of a state to wave vector of the state. There is a band of states then, with the width of the band dependent on the probability of hopping from one atom to the next. That's A. And for any k that we have, we can go and solve and find a solution that yields a constant energy in E, which is a function of k. And remember that k tells us how rapidly the phase of the wave function changes in space from atom to atom. So this, we've actually deduced a dispersion relation here, and it doesn't look anything like the kinds of dispersion relations that we've solved before, that we've seen before, but it does relate energy to wave vector. And we can take derivatives of this and find out what the acceleration and effective mass would be. Another way of approaching the solution of the dispersion relation is to assume that the electron has much greater energy, so it sits well above the potentials of the problem. And then we could estimate that the behavior of the wave function is going to obey a dispersion relation where it's essentially a free electron in the system. Okay? A free electron moving above a perturbing potential, which is periodic. And so we just have our normal parabolic band here where energy is equal to h bar squared k squared over 2m. That should be squared there, right? As in this picture here. That's what we would see for a free electron. Now we can ask, so my wave function for a free electron at a particular instant, the real portion, for example, is going to look like this. Okay? And then we can ask, how does that wave function lay on top of the atoms in the system? All right? Think of the wave function in a solid as consisting of a wave vector moving to the right and a wave vector moving to the left, so it forms a standing wave. And then that standing wave oscillates in time on the atoms or off the atoms. It could be that the probability of finding an electron on a particular atom is minimum, so that for a given wavelength, I have a minimum on the atoms. The standing wave is a minimum on the atoms, as shown here. Or I could shift the standing wave over and put a maximum probability of finding the electron on the atom cores. And depending upon which of these two situations I've got, standing wave on the atoms, standing wave off the atoms, I'm going to have higher energy or lower energy for a particular wave vector. And of course, that wave vector where the difference between on and off the atoms is most important is when the wave vector is equal to pi over the distance between the atoms, so that I have a repeat that appears on the atoms. When the wave vector is very different from that, then I have, let's say, I might have a standing wave maximum on this atom, but it's not on that atom, and then it's back on that atom. So only a fraction of the atoms actually have standing wave max or min on them. And as a result, the energy actually looks more like the free electron, the actual free electron. So we choose a point there, compare over there. Only when the wavelength of the electron in the system, the wavelength of the standing wave, corresponds to pi over the distance, or the wave vector is pi over the distance between the atoms, then I have this special case where I can have the standing wave on the atoms or off the atoms and have a difference in energy. So that splitting there is something that we can calculate, and the shape of the wave function can be solved using perturbation theory. We're not going to do that here in this course. It's just making the point that we can get an idea of what the dispersion relation looks like if we think about a free electron propagating through the material and making a standing wave that's on the atoms or off the atoms. So again, it's computable. So here's just a bigger sketch of what we were talking about on the previous page. The dashed line here is our free electron model. Then we introduce the periodic potential as a weak perturbation on the periodic model and find that depending upon whether the standing wave is on or off the atoms, I have a high energy or a low energy for that particular wave vector. And in this range here now, there actually is no electron energy that can be found. We're either going to find this one or that one. So that region between that point and that point is what's called a band gap, a forbidden band, where we won't find electrons at that particular energy. Here's a specific example of a calculation that we can do. It is highly simplified, and it is just to demonstrate to us how one might address a problem like this with a more complex potential. In the Kronig-Penny model, we either take our potential to be discrete delta functions on the positions of the atoms. All right, in this case, we're taking the delta functions to be repulsive, but it doesn't matter which we take, the solutions will be similar. Or in the Kronig-Penny model, very frequently, the solution has to do with a square well model. And during class, we'll actually look at a simulation using square well. All right, so here's our potential, delta functions. We're going to actually solve the Schrodinger equation in this circumstance where we've got a periodic potential, which is periodic with a distance a between the atoms. So all we've written here is the time-independent Schrodinger equation. The potential repeats on a distance a, okay? And we're going to take this to be a one-dimensional potential with delta function potentials that have a particular strength for the delta function. So this product out front is just to make the arithmetic work out more easily later on. So that's the assumption that we're going to make about the potential. So we just, on the previous page, we just had the time-independent Schrodinger equation, which I'm reorganizing somewhat in order to make the arithmetic a little bit more straightforward. So on one side, I've got my second derivative of the wave function with respect to space. So that would be a kinetic energy term, right? And on the other side, I've got the potential and the time-independent energy term, okay? And the potential is going to look like this. I've just sort of reorganized the constants so that 2m over h bar squared times the potential as a function of position, right, is a scaling constant, the distance between the atoms. Again, this is just scaling to make the delta function arithmetic work out well. And then our delta function potential. We take this relationship here and integrate once in x from one side of one of the peak of the delta function potentials to the other side. So I'm going to go from slightly less than 0 to slightly more than 0, okay, in terms of the integral. And the right-hand side is the same thing. We're going to integrate over the same range. I'm going to make the difference in position between the left side and the right side of the integral, slightly less than 0 and more than 0, so small that the integral of 2m over h bar squared e psi dx, because psi has got to be finite, that term is going to go to 0, and I'm just left with my delta function. So I'm integrating only over the delta function. And when I do that integral over the delta function from just below 0 to just more than 0, property of the delta function is that the integral over the delta function is 1 times anything else that happens to be in there. So the integral over the delta function, because of the potential that I've got there, is alpha over a times the wave function at 0. So that's the right-hand side of the integral. The left-hand side of the integral, this, is the integral of d squared psi dx squared once, which gives me d psi dx, evaluated just above 0 and just below 0. So the difference in slope on either side is related to the strength of the delta function potential. We use a proposal by Bloch that the wave functions in a periodic solid, in a periodic material, are that wave function on each site, right, times a phase factor, and then plug that in, and looking at the time-independent Schrodinger equation between the atoms, where the potential is 0, we've got a very simple relationship. This should be d squared psi dx squared plus capital K squared psi is equal to 0. Capital K is related to the energy. And between the atoms, all right, between the delta functions, the wave functions have got to look like this. Amplitudes, but sine kx and cosine kx. We obey the fact that the slope on one side of a delta function must be related to the slope on the other side according to the integral through the potential. And we have boundary conditions then above and below the wave function at 0 that correspond to the wave function itself being continuous. So the wave function on the left side of 0 must be equal to the wave function on the right side of 0, and that the slope must be behaved in the way that we just calculated. That gives us 4 conditions. We plug those in. We end up with this relationship between the wave function, let's say, in one location, n plus 1 location, and the wave function in the n location, right, in the box, the nth box between delta function potentials. And I end up with relationships that tell me the relationships between the A's and the B's. Making substitution for e to the I k x using the Bloch relations, we end up then with a relationship here after we've done quite a bit of arithmetic. It's not trivial, where cosine of, on the left-hand side, we've got the wave vector which relates how the phase between, how the phase changes as a function of position, so we call that the wave vector, and the term that is related to the kinetic energy. Capital K is still a wave vector, but it's the wave vector between the potentials. And this is related to the energy between the potentials. That's what I've got here, the energy of the state, h bar squared k squared, capital K squared, over 2m. When we plot that relationship, how does cosine of wave vector Ka, compare with cosine of square root of energy Ka, right? It ends up looking like this, plotting energy, capital K A squared is going to be related to energy, and phase wave vector, which is down here. We end up making a calculation which shows that the energy changes as a function of wave vector in the following way. This is the result of what's called the Kronig-Penney model. There are allowed bands, allowed wave vectors here, where the energy exists for a given wave vector, and there are regions where there's no energy for a given wave vector. And these regions are called band gaps in the material, and these are allowed bands. And when we look at the way in which energy changes with wave vector, we can deduce the effective mass of an electron moving in that system.